Okay, hello everyone, and welcome again to the first seminar of the new year. And today I want to kind of expand a bit on a topic that I touched last year at our research meeting, which is the topic of self-supervised learning. And this will be hopefully not very long presentation, which will just go on the more high-level introduction on the topic. And also, while my work is on graph representation learning, in this presentation, I will not talk about that, but I will talk about self-supervised learning from the perspective of natural language processing and computer vision, because these are kind of areas where it's easier to reason about what we are doing, because we all understand sentences and images better than we understand abstract graphs. And also because these are the fields where self-supervised learning has been introduced and where it is at, let's say, the most advanced levels. So I will start with what I was talking about last time. So I gave this very brief presentation of how supervised machine learning works. And let me find that pointer. And yeah, and I gave this schema where I said, okay, in a deep learning supervised model, what you do is that you have your input data and you pass it through a series of learnable transformations that produce what we call embeddings, that produce these latent representations of our input data. And the more we proceed forward, the more our representation abstracts away from the input data and towards what is our final objective. And if we take this and kind of abstract away from it, what we can think, we can see it as two parts. A first part, which is a deep encoder composed of several layers, which takes our input data and maps it to this latent space. And then after which would be in our case H2, and then after this, we have what we could term a shallow decoder, which is a simpler, smaller model, which takes this pre-computed information, takes these representations that already capture the key phenomena in the input, and very easily makes a prediction of whatever we are interested about from these already, let's say, pre-digested inputs. And if we have a supervised system where we are trying to predict some kind of, for example, we are trying to do some kind of classification. For example, we want to distinguish our data points into class A or class B, then what will happen is that because we are training this model end-to-end, so because our output performance affects all layers of our model, what will happen is that the encoder will learn to place our inputs in this low-dimensional representation in such a way that it becomes very easy to recognize, for example, what is A, what is class A, and what is class B. But this comes with some limitations. And so the first limitation is that very often we don't have enough labeled data to achieve our goal. So deep learning models in general require huge amounts of data. And when we work with supervised learning, we need huge amounts of labeled data. And while we reach the point where collecting a lot of data is relatively cheap, because we can automate the process, labeling data is very expensive and it's hard to automate. Because if we need, for example, to classify photos and say if it's a cat or a dog, well, you need to know if it's a cat or a dog to train the model. But then how can you say at the beginning if it's a cat or a dog if you don't have the model? You end up having to do it manually. So that's why labeling data is very expensive. And so often the problem is we can't really train our model to the performance we want because we don't have this data. Another possible reason we don't like this approach is that maybe we want a multi-purpose model. Maybe we want to use a single deep encoder with different decoders, because we want to answer multiple different questions from the same input data, we could, of course, do that with multiple deep models, but that might be too expensive to do because training these models is expensive. Can't we instead train a single deep encoder that captures all the different phenomena in our data in a way that is not biased by one task? And then we can so reuse it with different decoders to answer different tasks. And this also allows us to support tasks that we don't know about. So if tomorrow our boss comes and says, okay, now we need to predict this new thing on our customer data, we are able to do that without having to build a completely new model. We just need to add one more decoder on top of our already very advanced, very deep encoder. And then the final motivation is that maybe we don't have a task we want to answer. Maybe we just want to organize our data. Maybe we just want to do some clustering of our data. But our data is not something that we can cluster directly from the features. So maybe we want to process this data through a deep encoder that again extracts these important phenomena. And then we can cluster over these phenomena. We can cluster over this latent representation. And so in these cases, we can't really use supervised machine learning. And this is basically where self-supervised learning comes to the rescue. So in self-supervised learning, what we do is that we try to organize that embedding space based on the similarity of our input data points. So we do this without requiring any task-specific labels, and we do this without inserting any task-specific bias in the way we organize the data. So the data will not just split based on cat or dog, for example, but over multiple dimensions, we could see other kinds of splits. So is it an indoor picture or is it an outdoor picture? So we can do this, and yeah, exactly. We can capture different dimensions of this kind of similarity. How are pictures similar? Are they similar because they are pictures of the same animal? Are they similar because they're taking the same house? And so we can end up with something like this, where we have our embedding space. In our embedding space, we might have some points that are extremely similar. We might have some points that are instead very distant from each other because they are very dissimilar pictures, if we're talking about pictures. But we might also have situations where you can see, for example, these two input data points are similar based on this axis, and these other two data points are similar based on this other axis. And so we can see there is some dimension of similarity between these points, but also some dimension in which they have differences. And so this is basically what we're trying to capture. And now some of you might start thinking that this smells a lot like unsupervised learning. And this is where the situation gets a bit messy, because you can find a lot of confusion if you start searching online about unsupervised learning and self-supervised learning. And honestly, I'm not gonna give a definitive answer of what is one and what is the other, and when should you use the term unsupervised learning, and when you should use the term self-supervised learning. So what my understanding is that there is a lot of overlap between these two terms, and we could maybe consider self-supervised learning as a subset of unsupervised learning. But the problem here stems from the fact that unsupervised learning itself is a very general term that collects a lot of very, very different techniques. And so, for example, unsupervised learning also includes techniques that are not the domain of deep learning, like simple clustering of the features. So people, I think, came up in the last few years with this term of self-supervised learning in an attempt to have a better name, a more meaningful name for this subset of deep learning that tries to produce these general embeddings without having access to labels. And the focus here is on having deep models, and the focus is on the fact that we are not really unsupervised in the sense that it's not that we are missing some supervisory signal. We have a supervisory signal that guides our training, but that signal does not come from additional information like labels, but it comes from within our unlabeled dataset itself. Our dataset itself contains all the information necessary to guide our training and to supervise our training. But yeah, it's a bit of a messy situation. The term self-supervised started in computer vision, which is a field that does not really have a strong history of unsupervised techniques. But then this term also applies very neatly to natural language processing. And natural language processing was actually using techniques that we can now call self-supervised before the term self-supervised came into play. And at that time, they were, of course, calling them unsupervised techniques. And so the NLP field was already doing it with a different name and keeps doing it with a different name. But then we also have fields like graph representation learning, where we kind of adopted self-supervised learning recently, and there has been a lot of research on it, but still we have a long tradition of unsupervised techniques. And now there is this situation where some people are starting to rename some techniques that were traditionally unsupervised to self-supervised, but it's not clear where the cutting point is there. So overall, this is a very philosophical question, but it kind of becomes important when you need to search for papers or when you need to understand what a paper talks about. So yeah, in case you are interested and in case you end up looking around for self-supervised learning, yeah, be aware that there is this kind of situation where it's a bit ambiguous with unsupervised learning. What is what? And different people might use different terms. But after this quite long tangent, let's go back to self-supervised learning, and let's go back to how does a self-supervised learning model work? What steps do we need to take to build it? And now this is going to be the most tautological slide ever, because our goal here is to capture similarity and dissimilarity. And so what I'm going to tell you is that when you build a self-supervised learning model, you have to make sure that you minimize the distance between similar inputs and you maximize the distance between dissimilar inputs, which at first glance is, well, pretty obvious. That's exactly what we've been saying. Similar inputs have similar embeddings, dissimilar inputs have dissimilar embeddings. But then one question that might arise here is why do we need to do both of these things? Why can't we just say, look, we minimize the distance between similar inputs. So if these three inputs are similar to each other, they will move towards each other in the embedding space. And if these two are similar to each other, they will move next to each other because they are similar. And then it will, of course, a gap will form here between them. So why do we also need to do this second step, which is maximize distance of the similar inputs? And the answer is that while machine learning models in general think in a very different way than us humans, they actually share a very bad trait with us, which is laziness. So what will happen is that if you start training a model to give you the same outputs if you give it similar inputs. So for example, if you give it two pictures of two different lions, you want the same output. But if you give it a lion and an elephant, you want two different outputs. What the model might actually do, because it is lazy, is that it might say, look, you give me a lion, I give you the answer 42. You give me another lion, I still give you the answer 42. The answers are very similar, so you're happy. But if you give me an elephant, because I'm lazy, I will still answer you 42. It's very easy for me. I just learned to answer 42 all the time. And if I do that, of course, similar inputs will get similar outputs, but we will not have the second property. So it's not automatic that if you bring similar inputs to similar outputs, it's not automatic that you will bring them away if they are dissimilar. So you might end up with what we call a collapse, where everything according to the model is similar to everything. So that's why we need to make sure that we work on both these aspects when we build our model. And so let's go through these aspects one by one. How do we capture similarity between different inputs? And now let's make an example from natural language processing. Let's say that we are trying to build embeddings for words. And so what we can do is that we can take a sentence with a blank, so a context like this, where the blank is hunting the zebra, and we can ask ourselves, what can fill that blank? And if we think about it, we might think, maybe it's a cheetah hunting a zebra, or maybe it's a lion hunting a zebra. And the answer that we as humans might want to put there are all words that are similar to each other. Cheetah and lion are similar words, and they both fit here. And so we can train the model with this notion. So words that fill blanks in similar contexts must be similar. So if the answer here is cheetah, the cheetah is hunting the zebra. And then we have another sentence, which instead is the lion has just caught a zebra. That is a very similar sentence, and it involves a lion. So the model can learn that lion and cheetah must be similar because they appear in similar contexts. And so this is what we might call a context-based similarity. However, we are, in a sense, cheating here because we are building word embeddings, but we are using extra information other than the words themselves. We are using this extra information of in which context different words appear. We kind of have, in a sense, some sort of labels that come from our data set, which is the fact that cheetah and zebra appear together. And so what do we do if instead we don't have this? Because this is kind of borderline self-supervised. What if we don't have this extra information? For example, what if we're trying to decide if two sentences are similar to each other? But now we don't have a context anymore. We don't know where these sentences come from. We don't know which sentences appear next to each other. So how do we do in that case? And then one approach that is kind of the basic approach on which most natural language processing nowadays is built is the idea of perturbation-based similarity. So the idea that we can take a sentence and we can corrupt it, we can perturb it. For example, we can, again, put some blanks, or we can even take some words and replace them with totally random words that have nothing to do with the original sentence. If you think about it, we as humans have a pretty resilient reading skill. If you take a sentence and remove some words or replace them with random words, we can still understand what is the overall meaning, and we can even reconstruct what is the original sentence. We can easily read it if there are typos in what we are reading. And so the idea is that we can build something similar. So we can actually build a system that can take this perturbed sentence and you can embed it in a low-dimensional space. And then we can take this embedding and with a decoder, we can turn it back into a sentence that should be as similar as possible to the original sentence. And if we do this, what we are implicitly capturing here, what we're implicitly capturing in these embeddings that we produce out of the corrupted sentences is actually sentence similarity, because similar original sentences will produce similar corrupted sentences, and different corruptions of the original sentence will be forced by our loss function to bring back the original input, and so will be brought closer to each other in the embedding space. So in this way, we are actually capturing the sentence similarity. And I think this is actually one of the key aspects of self-supervised learning, this concept of data manipulation, where we take our input data, of which we don't know much about, and we manipulate it so that we have something we can reason on. So a manipulated sentence, a perturbed sentence, is similar to the original sentence. And this does not require any extra knowledge of the original sentence. And if we go to the field of computer vision, we actually see a slight variation of this, because here we need from the embedding space to go back to the original space of the sentence, which is easy to do. And then we have to compare sentences. And this is kind of easy to do for sentences. It's easy to compare if two sentences are similar. And it's easy to convert an embedding into a sentence. Much harder and much more expensive it is to convert an embedding to an image. And we don't have a clear notion of how similar two images are. And so once we go to image, to the field, to domain of computer vision, we use augmentation-based similarity, where we take two different views of the same picture, two different augmentations of the same input. For example, in this case, the right side is more cropped than the left side, but you could also add rotations, or you could make it grayscale. Basically, do some transformations to the input that still preserve this notion of similarity. Apply your neural network to both augmentations to obtain two embeddings. And then what you can do is that you can compare these embeddings. You can say these two embeddings should be similar to each other because the input images are similar to each other. And so this is kind of the most important aspect. We need to build these augmentations, these different views of the input that are different in terms of actual numbers and pixels, but represent the same concept, so are conceptually similar, so that our model can learn to bring them to similar locations in the embedding space. And so this is basically how we capture similarity. But then there is, oh, and by the way, when you have this architecture with two neural networks running side by side, that's what we often call Siamese networks. And now that we know this, we have to move to the second part, which is how can we capture instead dissimilarity? So how we can prevent our model from giving always the same output. And here, the straightforward approach is that of contrastive learning. And so also contrastive learning, a concept that was out there well before self-supervised learning became a thing. And so if we go back to our example, where we have the sentence about hunting a zebra, well, we told our model that cheetah is the correct answer. And then what we can do is that we can take a few other words and tell our model that those are not correct answers. So train, not a correct answer. D, not correct. Snowing, also not correct. And so what we are telling the model in this way is that these other words, like snowing, for example, they do not properly fill this blank. And so the word snowing is not similar to the word cheetah. And so in this way, the model can understand this, and the model can therefore build a system in which the word snowing has a very different embedding than the word cheetah. However, again, as I said before, this is cheating. We are using sentences to build word embeddings. What if we don't have sentences? What if we have images? What if we have images? Like, how do I do it? Which images are different than these? And so basically what you do is that the very simple approach of negative sampling, you just pick another random picture. So let's say in this case, a lion, and you can do the same thing. You have your two versions of your lion, you pass them through your Siamese network, you get two representations that should be similar to each other because they're both representations of the same lion. But then what you can do at this point is that you can say, aha, but then if I take any of these two chess representations and I compare it with any of the two lion representations, well, they should be different because chess pieces and lions, they are not the same thing. And so therefore, we train the model to say, look, these two are similar, but these two not similar. And the first one here and the third one here also not similar. And the second and the fourth also not similar. So this is the basic approach. And this is clear how it works and why it works. And it's relatively straightforward to implement. However, there are some issues with it, especially in the domain of computer vision, while in the domain of NLP, it works pretty fine. And the reason is that these domains are quite different. In NLP, here, if we're working with words, we only have a limited amount of words in our vocabulary. How many words does the English language have? I have no idea, but I guess no more than 1 million. On the other hand, how many pictures might you have in your data set? You might have hundreds of millions of pictures. And also, while the 1 million words are all the words, your 100 million pictures are not all the pictures. There are not infinite pictures because you have limited resolution, but there is a huge amount of potential pictures out there. And so you have a way higher dimensional space when you're dealing with pictures than when you're dealing with words. And what this means is that while taking a few random words as negative examples might be sufficient for the model to learn properly, on the other hand, just comparing our chess pieces with 3 or 4 or 5 pictures of other topics might not be enough for the model to actually learn how the pictures differ. You need to give a lot of negative examples. You need to have hundreds of pictures that are different from your chess pieces in order for the model to be able to learn the difference in such a high dimensional space as the one of pictures. And so it becomes very expensive to do and way more prone to bias in your input data, where your input data only contains certain classes of pictures and not others. And so because of these limitations of both cost and potential bias, there is a lot of research going on right now about avoiding contrastive methods and switching, for example, to non-contrastive methods. And so what does it mean? Well, here is where I will not really go into much detail, and I will just say that it's mostly dark magic, and even the people who work in this field don't always agree as to why certain approaches work and others don't work. So they've kind of come up with a set of guidelines for how to build non-contrastive models, at least in computer vision, but it's not 100% clear why they work and why other things don't work. But the key idea is that you want to use some kind of pivot to prevent collapse of the model. So you don't want the model to give you embeddings that are taken from anywhere in the embedding space, but you want to constrain it so that the embeddings must be built around certain pivot points in your embedding space so that they cannot all collapse to the same position, because they must stay close to their pivots. And so here there are really a huge amounts of different approaches. But so, for example, this is the same picture that I had before, just taken from a different paper. So we have the same model twice, and we pass the 2 inputs, and we get this output. And this is a contrastive approach. In non-contrastive approaches, what we have is that the right-hand side, so one of the 2 copies of the model, is actually different from the original model. And so what we are doing is that we are actually doing a different transformation and getting different embeddings for the different inputs. And we are using one of them as the pivot to train the models. So the right-hand side in these models is not trained in the normal way, and it's almost fixed. And the left-hand side instead is trained to produce embeddings that are as good as possible and do not stray away from the pivot points that are established by the right model. Or alternatively, another paper proposes another approach in which instead there is a set of pivot points that is used by two identical models, but these two identical models, they use this set of pivots to constrain their representations according to those pivot points. But again, so this is dark magic as far as I'm concerned, and we are not going into the details of this. But so these are approaches that are still very much in their infancy, but are interesting because they allow you to work on higher dimensional inputs like videos or complex time series, while avoiding the problems of large negative samples, populations, or bias based on your data set. And finally, a few key takeaways from what we went through. So the first one is that self-supervised learning is a very powerful and very flexible approach. And if you're working with machine learning in any way or form, I strongly suggest having a look at it because it might actually turn out to be useful for you. It is task agnostic, as I said. It can work on any task for the downstream, and you train it in advance without knowing what your task will be. And in a sense, it's conceptually domain agnostic because while I talked mostly about NLP and computer visions, the same structures, the same models can be applied to many other fields. Many approaches from computer visions are currently being applied to graphs with good success rates. And also there has been work on time series, on doing time series processing with these same techniques. However, while conceptually the architectures are kind of domain agnostic, building a good SSL model is very hard and requires a lot of domain knowledge. Why? Because the data augmentations or data perturbations that you use, those are very much domain specific. And as you might have guessed, they play a key part in making self-supervised learning work. Without good augmentations, you won't get good results. Also, you might need to do some choices when you build your model structures. For example, I showed you a few different approaches for non-contrastive learning with different ways to have these pivots into the model. But even with contrastive learning, there are several different choices in how you structure the layers of your model, and also how you choose the specific loss function that you use. And overall, there are tons of different architectures out there. So it's a lot of things have been tried. They work in some cases and they don't work in other cases. So it's not simple to actually achieve good results. And finally, self-supervised learning is a very young field. It's been out there. I mean, we could say that these approaches that now we call self-supervised, they've been there for a long time, especially in some fields. In natural language processing, they've been using these kind of approaches well before the term self-supervised learning was even coined. But in terms of a systematic study of the field, also abstracted from the domain, we are still at the early phases. We don't really understand all of the details of why certain approaches work and others don't. And this is especially true when you go to the non-contrastive approaches. Very interesting, but still hard and unclear how they work. But so this is the end of my presentation. Thank you very much for listening. I hope I didn't confuse you, and I hope I gave you some pointers to start understanding self-supervised learning. And if you have any questions, feel free to ask.